video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercise. Master each topic is to use the module's component together, view the program, read the manual, and work the exercises.
Producing oil and gas wells have two conflicting characteristics which challenge engineers. The tubing and completion equipment which connects the formation to the surface is generally difficult to alter once it's been installed. But the range and severity of producing conditions during the life of a well practically guarantee the need to replace or repair the equipment. Wireline operations permit repairs or revisions to the subsurface completion without the need for removal of the tubing and the expense that would entail, particularly at off locations. Wireline also permits routine data gathering and sampling activities and generally provides a means of physical contact between the operator and the distant subsurface. Here at the Baker Training Center test well, we see the equipment requires wireline. It's fairly straightforward. A steel wireline, of course, a system for bringing it to and out of well, and the appropriate assembly of piping and connections to permit pressure off to enter from the tubing. Also required are a device for accurately measuring the length of wireline in the well, another device to measure the force being pulled by the wireline, and a series of tools which can be easily and quickly attached to the end of the wireline to perform the necessary subsurface activities. In this first unit, we shall follow the rig-up of a typical wireline system and become familiar with the basic equipment. In the following unit, we shall cover the subsurface completion components designed for wireline operation and the manner in which wireline may be used to solve subsurface producing problems.
When a wireline crew and the wireline equipment arrive at a well location to perform wireline service, there will be numerous pieces of equipment that must be assembled before wireline operations begin. First, the connection on the wellhead must be adapted to the connections used on the wireline equipment. The lubricator sections are laid out and assembled next to the wellhead.
The lubricator is the sectional pipe used to contain the tools during entry and exit into the tubing. With the gin pole in position, the wireline valve may be lifted and placed in position on top of the tree, where it is made up to the tree connection. If a situation should arise that requires the well to be closed at the surface while wireline is in the well, the wireline valve may be closed without damaging the wireline.
The tool string is assembled and slid into the top of the lubricator, leaving about 1 foot sticking out of the top of the lubricator. The wireline is threaded through the stuffing box and attached to the wireline socket by tying a knot in the wireline. The wireline socket is screwed onto the tool string, and the completed tool string is pushed completely into the lubricator. Now the stuffing box can be attached to the top of the lubricator sections to complete the lubricator assembly. The stuffing box seals off around the wireline to contain the well pressure in the lubricator stack.
Before the lubricator can be lifted into position on the wellhead, the tool string must be secured in the lubricator so it cannot fall out while the lubricator is being lifted. The wire is clamped to the lubricator with a wireline clamp. Next, the lubricator is lifted into position above the wellhead with the rope falls. A shiv is attached to the tree, and the wireline is threaded through this shiv. The slack left in the wireline is reeled onto the reel of the wireline unit, and the clamp is removed from the wire. The tool string may now be lowered out of the open lower end of the lubricator and the proper tool attached to the bottom of the tool string. After attaching the proper tool, the tool string is pulled up into the lubricator and the lubricator attached to the wireline valve.
Before opening the valve on the tree to begin wireline operations, the entire lubricator stack should be tested. If any leak is detected during the test procedure, wireline operation should not be begun until the source of the leak is identified and corrected.
Let's look at some of this equipment more closely. First, the wireline itself. Wirelines are available in a variety of sizes, commonly stated in inches in diameter. The most common wire sizes are 0.082, 0.092, 0.105, and 0.108. The diameter of the wireline relates directly to its minimum breaking strength. The larger the wire size, the greater the strength of the wireline. The approximate minimum breaking strengths of the various sizes of plow steel line are shown in your manual. When exceptional strength is required, a braided wire line is used at low pressure situations.
However, there are other factors that affect the strength of the wire line. When wire line is run into the well, it must make a number of bends as it comes off the reel and makes its way to the well. This bending of the wire line tends to take its toll over time and causes the wire line to become work hardened. So wire that has been worked is not as strong as wire that is new.
Generally speaking, 80% of the minimum breaking strength is considered to be the maximum working strength of a wire line. But even that safety factor is no guarantee that the wire line won't break. A wire line, like a chain, is only as strong as its weakest link.
Wireline units come in a variety of types and sizes and are available from many manufacturers. They may be mounted on trucks or trailers for land locations, boats for inland waters and shallow offshore locations, or may be self-contained compact units for use offshore. They are all designed for one purpose: to allow the tools and wire line to be lowered into and retrieved from the wellbore.
The reel systems used on wireline units must have a power supply, which may be a diesel or gasoline engine, or an electric motor. This power supply may run the reel directly, or else operate a pump to supply fluid to a hydraulic motor. Most modern wireline units use hydraulically operated reel systems, which gives the wireline specialist the precise control needed to perform sensitive wireline operations.
The most common depth measuring device is a measuring wheel, which is connected to a feeder root counter. This device permits the wireline specialist to determine the measured depth at which the tools have reached in the well simply by seeing what depth is registered on the counter.
Immediately after leaving the wireline reel, the wireline is looped around the counter wheel. The wheel is precision machined so that when the wireline is wrapped around it, the circumference of the circle measured to the center of the wireline is exactly 2 feet. There are counter wheels machined for each size of wire. In addition to the counter wheel, there are 2 pressure wheels on the counter assembly, one mounted above the counter wheel and one mounted below. These pressure wheels keep the wire in place and minimize slippage.
The feeder root counter is attached to the shaft of the counter wheel either directly or via a cable, similar to an automobile speedometer cable. It is geared so that each revolution of the counter wheel counts off 2 feet on the counter. The counter has a key which allows the wireline specialist to zero the counter before lowering the tools in the well.
The weight indicator tells the wireline specialist the weight or tensional force that is being pulled on the wireline. As we'll see shortly, this information tells the operator many things about what is happening downhole.
The standard device for the industry is the Martin-Decker weight indicator. This weight indicator's primary component is a load cell, which is secured to the wellhead or some other equally secure location as close as possible to the tree. To the other end of the load cell is attached a sheave, which is called a hay pulley. The wire line from the wireline unit is strung through the hay pulley and continues up the side of the lubricator to the sheave on the stuffing box and on through the stuffing box to the wireline socket of the tool string. Inside the load cell is a fluid-filled diaphragm. When a load is placed on the wire line, the fluid inside the diaphragm of the load cell is compressed and the fluid is pressurized. The pressure is transmitted to a gauge mounted on the panel of the wireline unit, which gives the specialist a reading of the weight being pulled on the wire line.
In order to perform wireline operations on a well, it is necessary to be able to gain access to the wellbore and run wireline tools into the wellbore while there is pressure on the well. This is accomplished using the lubricator and the stuffing box.
Lubricator sections come in a variety of diameters and pressure ratings. The size of the sections used on a given well will be determined by the size of the equipment being run in the well and the size of the tool string being used to run the equipment. Lubricator sections are about 8 feet long for ease of handling and transportation. The lower lubricator section is normally larger than the upper sections to allow space for the larger diameter equipment that will be attached below the operating tool string. The lower sections of the lubricator must have ports for valves to allow the pressure to be released from the lubricator when the lubricator stack is to be lifted off the wellhead.
The lubricator, stuffing box, and wireline valve normally have quick union connections for ease of assembly. The quick union has 3 parts: the box, the pin, and the collar. To assemble the quick union, the pin with the O-ring seal is slipped into the box end of the quick union until the shoulder of the pin rests against the top of the box. Then the collar is slid down over the pin and threaded onto the box end of the quick union. The connection is designed to be made up by hand.
When the pressure is admitted into the lubricator stack, the pressure will tend to push the box and pin ends apart. The spreading action locks the collar, so that as long as there is pressure in the lubricator stack sufficient to keep the collar locked, the collar cannot be unthreaded from the box.
The stuffing box seals around the wire line and allows the tools to be run into the well with no loss of well fluids. Inside the stuffing box, the packing is held in place by two glands, one below the packing and one above. The gland above the packing is held in place by an adjustable packing nut so that the packing can be compressed to expand it against the wire. The packing segments are small cylindrical-shaped pieces of rubber or some other elastomer with a hole through the middle.
Anytime wire line is run into a well, there is always the possibility that something could happen that would require the well to be shut in while the wire is still in the well. The wireline valve permits the specialist to do this without damaging the wire line.
The wireline valve consists of a body, a set of opposing rams, ram stems, ram caps, and an equalizing assembly. The ram assemblies have rubber seals which seal around the wire line to contain the well pressure. The rams also seal in the body of the wireline valve to prevent well pressure from escaping around the ram when the valve is in the closed position.
The wireline valve is designed in such a way that when the valve is closed and pressure is released above the rams of the valve, the well pressure trapped below the rams holds them in a closed position. To reopen the valve, pressure must be equalized across the rams.
In order to accomplish wireline operations, we must attach to the wireline a tool string suitable to the well conditions and the work that is to be performed. The standard wireline work string is used to accomplish many functions.
The weight of the tools allows them to fall into the well bore with the force of gravity. The mass must be sufficient to overcome the friction of the wire line passing through the stuffing box and the force of the well pressure pushing up against the wire line where it passes through the stuffing box. The higher the well pressure, the tighter the stuffing box packing must be to maintain a seal, resulting in more friction. Also, the higher the pressure, the greater the force against the wire line cross-section in the stuffing box. The logical conclusion is that as well pressure increases, the tool weight must also increase.
When the well is drilled at an angle, the tools lay on the side of the tubing when falling into the well bore. This causes friction and requires that more weight be added to the tool string. Because of these factors, tool string lengths can sometimes be quite long. Long tool strings must also be somewhat flexible to allow the tools to pass through the tubing, which in many cases is not perfectly straight.
Of course, we must be able to perform work with the tool string once we position it in the well at the proper depth. Since we cannot rotate the tool string, and since wireline's small diameter limits the amount we can pull on it, wireline work is accomplished by delivering a series of hammer-like blows, either upward or downward, using the tool string. This is called jarring. And it is delivering this action which is the primary function of the tool string. Let's look at the components of a typical tool string individually.
The wireline socket provides the means to attach the tool string to the wireline. There are two basic types of wireline sockets. The first type requires the wireline specialist to tie a wireline knot to attach the wire. The knot is tied by looping the wire around the disc and wrapping the wire back over itself to form the knot. This type of socket is normally used on carbon steel lines with diameters of 0.092 inches and less. For larger diameter wire lines, another type of wireline socket is used. With this type, a wedge and a thimble are used to attach the wire line. The wire line is bent around the wedge and pushed back into the thimble. The body of either type of wireline socket is machined with an external fishing neck flange, which allows latching and retrieving the tool string if it should become lost in the well.
The stem provides the mass required for jarring operations and to carry the tools into the well. By adding or removing stem sections from the tool string, the wireline specialist can control the force of the impact being delivered downhole. The size and type of stem used is determined by the size of the tubing bore, the operation to be performed, and the amount of lubricator that can be raised over the well.
The jars allow the wireline specialist to deliver the hammering blows that are essential to perform most wireline operations. The jars are attached to the tool string below the stem. They look like two long chain links which can be slid together or apart. The distance that the two lengths can move from one extreme to the other is called the stroke of the jars. In practice, jarring can be done either up or down. To jar up, the tools are gently lowered until the jars are closed. By pulling up rapidly on the wire line, either by hand or with the wireline reel, the tools are moved to the top of the travel of the jars. When the jars open fully, a hammering blow is delivered upward by the jars and stem on tools attached below the jars. To jar down, the tools are gently pulled up until the jars are opened. Then, by releasing the wireline rapidly, the jars are suddenly closed by the weight of the stem falling. This delivers a downward impact to the tools below the jars. In this manner, the wireline specialist can deliver the hammering blows needed to perform wireline operations downhole.
Knuckle joints are used in the tool string to give the string flexibility. In crooked or corkscrewed tubing, this flexibility is important to allow the tools to pass through the tubing with a minimum of drag or friction between the tools and the tubing. At least one knuckle joint will normally be used directly below the jars in the tool string. This knuckle joint is used to allow the larger diameter tool or subsurface control attached below the joint to centralize itself in the bore of the tubing.
These, then, are the components of the standard work string: the socket, the stem, jars, and the knuckle joint. In addition to the specialized subsurface production controls run into the tubing with this work string, there are several other commonly used tools which may be run for routine operations. For example, the first step in performing any wireline operation downhole is to determine if the tubing is clear to the depth at which that operation is to take place, and if not, to clear any obstruction from the tubing. This is the function of the tubing conditioning tools, which are normally part of the service equipment used by the wireline specialist.
The tubing gauge cutter is normally run prior to any other wireline operation to check that the tubing is free of obstructions. These gauges are normally slightly smaller than the minimum ID of the tubing to allow the gauge to pass through the tubing but stop if any obstruction is encountered in the tubing bore. These gauges are beveled to remove paraffin deposits or light scale deposits from the tubing wall.
The tubing swage can be used to open up constricted places in the tubing if they are not severe. This tool is tapered on both ends to allow the tool to be jarred through an obstruction repeatedly until the tubing ID is returned to normal.
The tubing broach is also a tool designed to remove obstructions in the tubing wall. It is particularly useful for removing metal burrs from tubing ends that may have been damaged while tubing was being run during completion. The primary difference between the broach and the swage is the swage does not remove metal from the inside surface of the tubing, and the broach does actually shave metal away from the tubing.
The blind box is a solid metal tool used to hammer down on an obstruction when heavy downward jarring is required. It could be thought of as the head of a wireline specialist's hammer. The tool surface is flat and hardened, so it will not flare out on the bottom when it is being used to hammer on tools or other obstructions in the tubing.
The impression block is used to take impressions of hard or metallic objects in the tubing in order to determine their size, shape, and relative position in the tubing. It is an important tool to the wireline specialist when trying to identify tubing obstructions during fishing operations. It is made by pouring molten lead into a metal sleeve machined for this purpose. Once dressed to a smooth face, the tool is lowered to the obstruction and gently set down on it. Jarring down only once will give an impression of the object to be fished.
Pulling tools are designed primarily to be used to retrieve subsurface devices from the tubing bore. Such devices are designed and constructed to provide a place near the upper end of the device for a pulling tool to engage or latch the device so it can be unlocked and retrieved from the tubing bore. This part of the device is commonly referred to as a fishing neck. Some devices are constructed with fishing necks that require the pulling tool to go over the outside of the neck. Other devices are constructed with fishing necks that require the pulling tool to latch inside the fishing neck to retrieve the device.
Whenever a subsurface device is latched in the tubing bore, there is always the possibility that it may become stuck or that some other condition exists downhole, preventing the device from being retrieved from the tubing. All standard pulling tools are designed so that if such a condition exists, they may be released from the fishing neck to allow the tool string to be retrieved from the wellbore. This is usually accomplished by shearing a metal pin in the pulling tool. To shear the pin in some tools requires that the operator jar up with the tool string. Other tools shear with downward jarring. Obviously, the intensity of the jarring required to shear the pin must be greater than would normally be required to pull the downhole device.
In the process of designing downhole flow controls and other downhole devices to be used in oil and gas wells, it is imperative that these controls be designed to permit their placement at predetermined depths in the wellbore using wireline running tools. In general, these tools are attached to the flow controls by means of shear pins, collets, retaining dogs, or some combination of the three. When the desired depth is reached with the control attached to the running tool, manipulation of the wireline tools places the control in the set or locked position and releases the running tool from the control. This is usually accomplished by shearing a metal pin, which was then used to hold the control to the running tool. Because the design of these running tools is so varied, and many running tools are designed to run a specific control or device, discussion of the running tools will be covered with the discussion of the devices themselves and in more detail in your manual. Sometimes, in spite of our best efforts, the wireline breaks or tools become stuck in the wellbore. Often both wireline and tools are lost in the well and must be fished out. Let's identify now the common fishing tools and give a general explanation of their purpose.
The wire finder is used by the specialist to locate and coil the upper end of the wire line so that it may be retrieved with a wire grab. One type of wire finder is a soft metal cylinder which can be flared out to conform to the ID of the tubing in the well at the time. When lowered on a conventional wireline tool string, the wire finder will contact the top end of the wire line, and the specialist can coil or ball up the broken end of the wire, allowing it to be engaged much more easily with a wire grab.
Another type of wire finder uses a metal skirt, which is slotted to allow it to flex out against the tubing wall. The slotted cylinder will allow the wire finder to be run through reduced ID restrictions in the tubing and flex back out after passing the restriction.
Once the wire line has been located and the upper end coiled or balled, the wire grab is used to latch and retrieve the wire line to the surface. The wireline grab consists of 2 or 3 legs or prongs which are welded to a machined sub with a pin end and fishing neck. Upward movement of the tools causes the coils of wire to catch on the barbs, allowing the wire line to be retrieved to the surface.
The center spear consists of a pointed rod which has barbs welded on the OD of the rod. About the only time a center spear is used is when the wire line is balled so tightly in the tubing that the prongs of the wire grab will not move over the ball of wire to allow the barbs to grab it. Some tools are designed to both locate and retrieve the wire line during one trip in the well. These tools are called wire retrievers. The oldest and most popular of the wire retrievers consists of a mandrel, which has a spear point on the bottom and a slotted skirt which floats over the mandrel. The ID of the skirt and the OD of the mandrel are machined to have matching tapers, which, when the skirt moves down over the mandrel, will wedge the wire line between them and grab the wire.
A cutter bar consists of a wireline socket attached to the top 1 or more lengths of a stem and a blind box attached to the bottom. It is used to cut the wire at the top of the wireline socket of a tool string that cannot be retrieved from the well. In such an instance, the cutter bar can be dropped into the well bore where it will bypass the wire line and fall to the stuck tool string. The blind box on the cutter bar bends the wire over and mashes it against the wireline socket of the stuck tools, thereby cutting it and allowing the operator to retrieve the maximum length of wire line.
In some cases, the wireline specialist may choose to drop a Go Devil before the cutter bar. The Go Devil is used to provide a base for the cutter bar to mash the wire against. The Go Devil is slotted its entire length and is designed to be pinned to the wire line. After dropping the Go Devil, a cutter bar may then be dropped to cut the wire line at the top of the Go Devil after which the Go Devil can be retrieved.
The Kinley snapper is another tool designed to cut the wire line at the wire line socket. The assembly is allowed to fall into the well pinned to the wire line, and when the snapper strikes the wire line socket, the crimper and knife force the slipper to move sideways in the tool, cutting the wire line between the slipper and the knife. This action also crimps the wire line between the crimper and the clipper, which allows the snapper to be retrieved with the wire line.
Like the cutter bar, the snapper must have a solid base upon which to work to cut the wire line. If there's any doubt that it will be able to reach the wire line socket, a Go Devil may be dropped ahead of it in order to give it that solid base. Sometimes sand deposits or bridges will build up in the tubing and prohibit wireline operations. If this is the case, some type of baler may need to be run in order to remove these deposits.
Pump balers consist of a barrel, plunger, and baler bottom. In operation, the baler is stroked to create a suction which picks the sand up into the baler. To hold the sand inside the baler once it is picked up, the baler bottom is designed with a check valve, which opens on the upstroke to allow the sand to enter the baler, but then closes once the stroke is completed to prevent the sand from falling out the bottom of the baler. Although there are many designs of hydrostatic balers, they all use the same operating principle. The barrel of the baler is sealed with atmospheric pressure inside. Then the baler is run to the top of the sand. Downward jarring on the baler will shear a pin or disc, which opens the baler to the higher bottom hole pressure in the well bore. The pressurized well fluids rushing into the barrel of the baler carry the sand into the barrel where it is trapped by the ball check in the baler bottom.
Balers are often modified by the wireline specialist to remove junk from the well bore which is too large to pass through the baler bottom. By adding a junk basket to the baler bottom, gun debris, pieces of metal, rubber, wireline, or other types of junk can be picked up and removed from the well bore with the baler.
Certain tools and equipment are only used in special situations. However, these specialty tools are often essential to the successful completion of the wireline operation. For example, roller stems, stem sections with small rollers on them, can be used in highly deviated wells to reduce the friction of the tools lying on the tubing and improve tool string performance. Tubular jars, such as these here, are sometimes used in place of the link jars we saw earlier for some operations. They are made from a tube or cylinder which slides over a mandrel to deliver the jarring impact, like that. Hydraulic jars, or mechanical detent jars, such as these here, are used by the wireline specialist to deliver a harder jarring blow upward on stuck tools or subsurface controls than can be delivered with the mechanical jars. The tools covered in this section are generally considered to be the most common working tools of the wireline specialist. They are designed to allow the specialist to set or retrieve subsurface equipment within the tubing string. In the next unit, we shall discuss the basic types of subsurface flow control equipment for which these wireline tools are designed. For now, please read the first section of the manual and work those exercises. A primary purpose for wireline operations is to enable the operator to place a variety of flow control devices at various locations within the tubing string. These devices generally must permit flow or hold pressure in either the upward or downward direction. In order to accomplish this, the devices, or controls as we call them, must have a place to anchor and an attachment for locking them in place, a locking mandrel. Various systems have been designed to permit controls to be selectively placed in a particular location by varying the locking mechanism, the anchoring receptacle, or the running tool. Different manufacturing and wireline service companies have designed different solutions to the problem, and the result is a wide variety of unique selective wireline production control systems. In this unit, we shall try to summarize the fundamental differences and similarities among the most commonly used systems. We shall begin by discussing non-specific locking mandrels, and then the more specific locking mandrels and their receptacles, and finally the types of controls commonly installed using these systems.
Lock mandrels are flow-through devices used to anchor subsurface flow controls in the flow stream of the well. Lock mandrels will either anchor directly in the tubing wall in a collar recess or in a special receptacle provided in the tubing string. All locking devices have certain features that are the same. They must have a means to be securely anchored in the flow stream of the well. They must have a seal that will contain the pressure of the well. They must allow the attachment of a subsurface control. It must be possible to set and retrieve them in the tubing bore.
Tubing locks are lock mandrels that can be anchored in the tubing without any special receptacle being provided. Slip locks anchor and seal on the ID of the tubing, while collar locks, like collar stops, use the collar recess in API threaded and coupled pipe for anchoring the lock mandrel. The main advantage of the collar lock mandrel is the higher pressure rating for all sizes as compared to the slip lock. This is because the lock uses the collar recess on API threaded and coupled pipe as the locking profile. This provides a more substantial surface to support the lock mandrel. These locks are also capable of supporting a positive pressure differential from both directions.
In order to unlock and retrieve a tubing lock, it is necessary to equalize any pressure that might be held beneath the lock and its attachments. An equalizing sub is normally run between the tubing lock and the subsurface control for this purpose. The equalizing valve is held in a closed position by a spring and protrudes slightly into the bore of the body. To equalize the pressure beneath the lock mandrel, a prong is run attached to the pulling tools. The prong is run through the bore of the lock mandrel and pushes the valve open. Once the pressure has been equalized, the lock may be unlocked and retrieved.
The slip lock can be used to anchor plugs, safety valves, pressure regulators, or bottom hole chokes. These locks are usually limited to use in low volume, low pressure wells. This is because slip locks have a relatively small flow area through the bore of the lock and limited pressure ratings because the lock uses the tubing wall itself to anchor the lock, and the condition of the tubing will deteriorate with time. Most wells today are completed with future wireline work in mind and have a series of receptacles or landing nipples included in the completion string. These landing nipples are designed to permit specific locking mandrels, nipple locks, to be installed in the nipples. Most subsurface controls are installed using this equipment.
A landing nipple is a short section of pipe which is threaded on each end and installed as part of the tubing string during completion of the well. The landing nipple is machined with an internal profile to provide a place for a locking mandrel to lock into the nipple to anchor a subsurface control, as shown in these cutaway nipples. The nipple is also machined with a polished area below the locking profile, which is called the packing bore. The packing bore provides a smooth surface on which the seals of the locking mandrel can seal for pressure control in the well bore. Some landing nipples have an additional profile machined internally to locate the running tool for proper positioning of the lock mandrel during the running procedure.
The most commonly used landing nipples are available in two different types. These are selective landing nipples and no-go landing nipples. Selective landing nipples are essentially unrestricted nipples. Several selective nipples with the same internal diameter can be installed at different depths in the same tubing string. These nipples are called selective nipples because once they are installed in the well bore, we can select any nipple in the tubing and install a specific lock mandrel in that nipple.
What must be remembered is that the nipple, the lock mandrel, and in some cases the running tool used to run the lock mandrel together comprise a system whereby this selectivity is possible.
For every selective nipple system, there is a compatible no-go nipple that is designed to be used with it. A no-go nipple is a nipple that has a restricted ID as compared to the selective nipple of the same nominal size. Because the nipple is restricted, only one no-go nipple of a given size may be included in the tubing string, and it must be run beneath all selective nipples of the same nominal size for the completion to be compatible. A lock may be run through the upper selective nipples in the tubing until the no-go nipple is reached. The nipple is called a no-go because once the lock reaches the nipple, the shoulder of the lock no-goes on the restricted ID of the nipple, preventing it from passing through the nipple and simultaneously positioning the lock mandrel for setting.
The three most commonly used selective landing nipple systems are those designed by Otis Engineering, Baker Flow Controls, and Camco. Let's discuss each of these individually.
The Otis S-nipple has two profiles machined in it, the top profile being the locking profile and the lower profile being the locating profile. Between the locking and locating profiles is the polished packing bore. Up to 5 different locating profiles can be machined in the nipple. This means that as many as 5 different selective nipples can be placed at various positions within the tubing string during the completion of the well.
The Type S lock mandrel consists of 2 sub-assemblies, the locking assembly and the locating assembly. 5 different profile keys corresponding to the profiles in the 5 positions of nipples may be incorporated into the locating assembly. For example, if the locator keys used on the locator are position 3 keys, then the lock will only locate in the position 3 nipple. This is how the lock is able to select the nipple in which it is set.
Otis Type X equipment is Otis's running tool selective system. When selectivity is achieved with the running tool instead of the profile machined in the nipple, all the selective nipples in the tubing string can be identical. All Type X nipples have the same locking profile. All X nipples of the same size have the same hone bore ID. Because the nipples are identical and selectivity is determined by the running tool, as many nipples as desired may be run in the tubing string.
The design and function of the X lock is a little more complicated than the S lock. The position of the keys on the lock mandrel are controlled by double-acting springs. These springs either hold the keys retracted into the key retainer while the lock is being run in the well, or they move the keys out to locate the nipple once the desired nipple has been reached.
The key positions of the lock mandrel are controlled by the running tool, and the running tool used to run the X-lock is the Type X running tool. With the running tool in the running position, the keys of the lock mandrel are retracted in the running position. This allows the lock to be run through any or all nipples in the tubing string without locating. To locate the nipple the lock is to be locked in, the specialist must run the lock and running tool through the nipple and then pull them back upwards again for the nipple. This trips the running tool and spring loads the keys of the lock mandrel, thereby placing the lock mandrel in the locating position. Then the lock and running tool are slowly lowered into the nipple. The spring-loaded keys of the lock move out into the locking profile, and the right-angle shoulder on the keys catches the right-angle shoulder of the profile in the nipple.
Once the lock is located and locked into the nipple using a downward jar, upward jarring shears the pin holding the core of the running tool to the packing mandrel of the lock, which in turn releases the running tool from the lock and leaves the lock set in the nipple.
The XN nipple is the no-go version of the Otis Type X nipple. The X lock may be changed to an XN lock simply by changing the X keys, replacing them with XN keys, and adding a no-go sub. The XN lock is run exactly the same way as the X lock, with one exception. Since the XN lock cannot pass through the no-go restriction in the nipple to trip the running tool must be tripped on the last selective X nipple in the well. The XN keys on the lock will not locate in the profile of the X nipple, but will pass through it and allow the lock to be run to the XN nipple.
Camco equipment features running tool selectivity in sizes up to and including the 3.5-inch size. For larger tubing sizes, 4 or 7-inch sizes, all locks and nipples are no-go.
The selective Camco nipple is called the W1 nipple. The W1 nipple has a simple locking profile with a honed bore beneath the profile. The Camco Type M lock mandrel is designed for the W1 nipple.
The running tool designed to selectively run the M-lock mandrel is the W1 running tool. The M-lock is pinned to the running tool with 2 tangential shear pins, which pin the housing of the running tool to the dog housing of the lock mandrel.
Once the lock and the running tool are pinned, they are run in the well bore on a standard wireline tool string. Once the nipple that the lock is to be locked into is passed by the wireline tools, the tools are pulled back up through the nipple and then lowered slowly into the nipple again. The locator dogs now may spring out, which allows them to locate in the collar recess above the nipple. This positions the lock in the nipple with the locking dogs aligned with the locking profile. Downward jarring secures the locking dogs in the profile of the nipple. Upward jarring then shears the pins attaching the lock to the running tool and releases the running tool from the lock. The no-go nipple designed to be used beneath the W1 selective nipple is the D nipple, whereas the Otis uses a bottom no-go design with a no-go restriction located in the lower end of the nipple. Camco uses a top no-go design.
The no-go lock mandrel designed to lock in the D nipple is the Type C lock mandrel. The C lock is run with the Camco Type D running tool. It is equalized and retrieved using exactly the same procedure as is used for the M lock. A third manufacturer, Baker Flow Control, offers selective and no-go nipples and locks for tubing sizes through 4.5 inches and a no-go nipple system for tubing sizes from 5 through 7 inches. Baker's selective nipple is called the Model F nipple, and the compatible no-go nipple is called the Model R nipple.
The Model F nipple has a simple groove machined internally for the locking profile and a packing bore below the locking profile. The Model R nipple is similar in design to the F nipple, but has a no-go restriction machined into the nipple below the packing bore.
The Baker nipple system is a running tool selective system. As many F nipples as necessary of the same size may be run in the tubing string.
The Baker selective lock is called the S-lock assembly. Two of the locking dogs face up to support any pressure differential from below the lock, and two dogs face down to support any differential pressure from above the lock.
The simplest and most often used running tool is the C1 running tool. It is pinned to the S-lock by two sets of tangential shear pins. If the lock assembly is to be run to the uppermost F nipple of its size in the tubing, a locator ring, which will no-go in the nipple, is threaded onto the running tool. The lock is then lowered into the well bore on wireline until the nipple is located with the locator ring. Pulling the tools up allows the up-facing locking dogs to snap into the nipple profile. Upward jarring shears the top pins in the running tool and allows the running tool to move up in relation to the lock. Once the shank clears the heel of the down-facing dogs, these dogs snap out into the locking profile. Both sets of locking dogs, both up-facing and down-facing, are now locked in the nipple profile. Upward jarring now shears the remaining shear pins and releases the running tool from the lock.
The C1 running tool may also be used to set the lock in other F nipples, besides the top one of its size, by replacing the locator ring with a thread protector. Without the locator ring on the running tool, the lock may be run below the desired nipple and pulled up to it, allowing the up-facing locking dogs to locate the nipple. After locating the nipple, the same setting sequence is followed.
Another running tool designed to run the S-lock is called the Model E running tool. Once pinned to the E running tool, the S-lock is run in the tubing with wireline. The lock passes through the tubing and nipples because the locks are held retracted by a plunger in the running tool. Once the nipple in which the lock is to be set is passed, the tools are pulled back to the nipple. As the running tool and lock assembly are pulled upward in the nipple, the locks on the lock assembly snap into the locking groove in the nipple. Upward jarring then shears the pins between the running tool and lock assembly, which releases the running tool from the lock and allows retrieval of the wireline tools. The equalizing subs that are used with Otis and Camco equipment can also be adapted for use with Baker equipment. Baker also makes use of an equalizing sub which has a replaceable hollow plug that protrudes into the bore of the sub and is broken off with a prong to equalize the pressure before a lock may be unlocked and pulled.
Once equalized, the lock is unlocked and retrieved by running a probe, called a Model A probe, threaded into the core of the pulling tool. The A probe will retract the up-facing locks, but allow the down-facing locks to remain locked into the locking groove of the nipple. This allows the pulling tool to engage the fishing neck of the lock assembly without the risk of the lock assembly being pushed down and out of the nipple. Once unlocked and latched by the proper pulling tool, the lock is retrieved to the surface.
The Model R nipple is the compatible no-go nipple designed to be used beneath a string of F selective nipples. Available only in small bore sizes, the R nipple uses a restriction beneath the packing bore of the nipple to locate and support the lock in the nipple. The Type Z lock assembly is normally used in the R nipple. It is located and supported in the R nipple by a no-go shoulder machined on the subsurface control used with the Z lock assembly. Now that we have reviewed lock and nipple systems, we are ready to discuss some of the more common subsurface controls which are run using these systems. It should be remembered that the locks we have briefly discussed are used to anchor subsurface controls and would rarely be or ever be used alone. One of the most common subsurface controls that is anchored by the lock mandrel is the plug.
Plugs fall into three basic categories, depending upon which direction they hold pressure. There are plugs designed to hold pressure from below only, above only, and from both directions. Plugs that hold pressure from below only isolate the tubing and wellhead from the formation pressure. These plugs are used to allow removal or repair of wellheads and for safety applications when a well is not flowing but still has the potential to flow. This type plug usually is designed so that if the need arises, fluid could be pumped through the plug from the surface to kill the well.
Plugs that hold pressure from above only isolate the formation from pressure that is applied to the tubing. These plugs are used to test the tubing to circulate and displace well fluids and to set hydraulic packers. This type of plug is not usually set on a lock mandrel. Instead, it either locates in a nipple profile or locates in a no-go nipple to support the differential from above.
Plugs that hold pressure from both directions are designed to be used to isolate and separate two producing zones in a well. In such a situation, the pressure differential could be from either direction and could change as one zone is produced. Therefore, the plug used to separate two zones must be able to hold pressure from both directions to assure that the zones remain isolated.
In your manual is a discussion of various plug assemblies by category. The lock mandrel systems normally used to anchor these plugs is also identified. Another control device, the subsurface safety valve, is placed in the flow stream of many wells for protection against uncontrolled flow in the event surface flow control equipment fails or is damaged. In such cases, the subsurface safety valve is designed to close automatically.
The wireline retrievable safety valve is run and retrieved using wireline methods. It may be surface controlled or subsurface controlled. The surface controlled valve is run in conjunction with a lock mandrel to a special safety valve nipple. The nipple has two polished packing bores, one on either side of an entry port for the hydraulic control fluid. As long as pressure is exerted by the control fluid, the valve stays open to allow the well flow to pass through the valve.
A subsurface controlled safety valve is a wireline retrievable subsurface device which closes in response to changes in the flowing characteristics of the well. Two basic designs are in use: the differentially operated valve and the pressure operated valve. The differentially operated valve is a velocity-sensitive valve. The valve is held in the open position by a spring and is normally open. If the well is allowed to flow uncontrolled, the increased flow velocity creates a pressure differential across the beam, sufficient to compress the spring and close the valve.
The pressure-sensitive valve uses the existing wellbore pressure to control the safety valve. This type valve makes use of a pressurized dome or bellows which is charged at the surface. If the wellbore pressure drops below the dome pressure and spring tension, as in the case of high-velocity uncontrolled flow, the valve closes.
Another commonly used device installed using wireline is the gas lift valve. Modern gas lift installations are designed to allow gas lift valves to be installed and removed at various locations within the tubing string to allow the well to be unloaded or produced using gas lift.
The side pocket mandrel is used to hold the valves and is run as a part of the tubing string. It is usually full tubing bore through the bore of the mandrel and incorporates in the design of the mandrel an offset side pocket. This side pocket has ports which provide for communication between the tubing and the casing. The side pocket has polished packing bores machined above and below the ports and a locking profile in the upper end of the pocket. The major advantage of the side pocket mandrel is that when these devices are installed in the side pocket, full tubing bore is maintained.
Because the side pocket is offset from the center line of the tubing, it is necessary to devise a wireline tool string that can kick over into the offset of the mandrel when controls must be run or retrieved. This is accomplished by using a device called a kickover tool.
There are various designs for these kickover tools. Some require that special changes be made in the side pocket mandrels in which they're run. The main thing to remember is that not all kickover tools will work in all side pocket mandrels.
Another wireline-operated component similar to a side pocket mandrel is the sliding sleeve or sliding side door, by far the most popular and widely used tubing casing communication device. The sleeve is run as an integral part of the tubing string. and has an inner sleeve which, when positioned so that the slots of the inner sleeve align with the ports of the housing, will allow communication between the tubing and the casing. The inner sleeve is moved using a wireline-operated shifting tool. Some sliding sleeves are designed to be opened by moving the inner sleeve up, and some are opened by moving the inner sleeve down.
If the seals in the sleeve ever begin to leak, a flow control known as a side door choke may be set in the sleeve. The side door choke locks in the nipple profile of the sleeve and seals in the packing bores, located in the top and bottom subs of the sleeve. This prevents the leaking sleeve from communicating between the tubing and casing. The well can continue to be produced until the tubing is pulled and the sleeve replaced.
Another device that can be set across the sleeve allows communication between the tubing and casing while plugging the tubing area beneath the sleeve. This device is called a separation tool.
A pack-off is used to patch an internal tubing leak to allow the well to be produced until the tubing can be pulled and replaced. Pack-offs are run and retrieved using wireline methods. The pack-off consists of two sealing elements which are attached to either end of a spacer pipe. When run in the well, these two elements straddle the hole in the tubing and seal on the ID of the tubing. The seals on the elements are mechanically expanded against the tubing wall when the pack-off is set.
These are the most commonly used subsurface flow controls that are wireline operated. The procedures for running these devices are outlined in Section 3 of your manual. Also in that section are descriptions of sand bailing and fishing operations, two activities that, unfortunately, are often part of the wireline specialist's routine. Please read this section along with Section 2 carefully before working the appropriate exercises. You should then have a basic understanding of the complete range of wireline operations. Good luck.